Okay, so Unit 8.8, we're going to talk about buffers, and we're going to talk about how to create a buffer with stockroom materials. So at least that's going to get us started with that. So we've already introduced buffers. We've already introduced Henderson-Hasselbalch equation, and we're going to use that idea of the Henderson-Hasselbalch equation if we have a desired pH and we know a Ka for the compound for the weak acid, we can take the negative log of that to get pKa. Like maybe if we had, like, say we were trying to make a pH buffer of 9, and maybe we had a Ka value that was 1 times 10 to the negative 9th, the pKa would be 9. So this is going to be a very nice buffer here, and we'll talk about why that would be a really nice buffer. We could solve for this ratio. Okay, so 9 minus 9 is 0. When you take the anti-log, the anti-log of 0, you're not going to really get very far, but this is going to give you a ratio of 1 to 1. What that means is that you need 1 molar A minus for every 1 molar HA. It could also mean, since they're in the same beaker, 1 mole per 1 mole. Now, if you were actually going to try to dissolve a number of grams into a container that would be 1 mole, that might be very difficult. So lots of times people will take this ratio, this 1 mole to 1 mole in this case ratio, and maybe divide them by a certain number. If they do that, they keep the ratio intact, but make it much more manageable as far as numbers are concerned. So maybe like 0.01 divided by 0.01. Now you could take those moles and turn them into grams, and those grams possibly could be a small enough grams that you could actually dissolve in water. Maybe you're trying to make 100 milliliters of this solution. So you can't dissolve an unlimited number of grams in a certain volume. So sometimes you might have to manipulate that ratio to get it into some kind of manageable number. Okay. So we've talked about buffers a number of times. The best buffer is something that's going to have lots of A minus and lots of HA. Those two components you need to be able to neutralize acids or to neutralize bases. Here is a good example of a buffer. Ammonia, by the way, comes in a solution, and then ammonium chloride comes in a dried form. It's probably it's a white powder or a white salt, and we're only interested in the ammonium part of it. The chloride is just going to float around, has no impact on water because the chloride is related to hydrochloric acid, and so because it's related to a strong acid, it has no effect on water. Same example, I have a weak acid, acetic acid, and I have acetate. And so that would be my HA and A minus. The sodium ions are related to sodium hydroxide, a strong base. So that's not going to impact the pH of water. Here's a couple buffers that you might notice. Let's look at this one here. So carbonate, CO3 minus 2, and bicarbonate. Actually, let's not talk about it that way. Let's talk about carbonic acid and then bicarbonate. That would be a really nice buffer. So this is your HA and this is your A minus. Okay. Oops. There's lots of buffers as you get further on in biochemistry or organic chemistry that you might investigate. We're definitely going to use the Henderson-Hasselbalch. We would love that we can find a pKa that is closest to our desired pH that we want to make of our buffer. Unfortunately, these aren't, there's not an infinite number of buffers, and certainly not an infinite number of buffers, buffer materials that are going to be in anyone's stock room. So often these pH to pKa aren't going to be perfect numbers. But the best would be if our pKa would match up with our pH. If you would get a possibility where maybe pH, you were trying to get a desired pH of 9, and then you got a pKa of 4, that's going to be very problematic. And I'll show you why. So let me solve for that A minus versus HA if you do that. So 9 minus 4 is 5. And then take the anti-log, and that's going to give you that ratio. So what's going to happen is that if you get that A minus number down into a manageable number that you could actually get to dissolve in your solution, you'll have an HA number that'll be so infinitely small that you basically have hardly any HA. So it will be, you'll have lots of A minus, and you'll have virtually no HA. So that's not a good buffer. Okay, which of these would be buffers? So for you to have a buffer, you need to have a difference of 1 H positive from each other. So if we decide we were going to use phosphoric acid, we would need something that has H2PO4 minus. That does not have H2PO4 minus. It has PO4 minus 3. So that would not be a good buffer. HF, we would need over here F minus. Well, we don't have F minus, we have ammonium, so this is not a good buffer. Phosphoric acid and H2PO4. Bingo. H2PO4 and PO4. That's not a difference of 1 H positive. So that's no good. This would actually make a precipitate if you tried to combine calcium ions and carbonate. So that's not a good buffer. HPO4 and PO4. Now, with all these, I've neglected the charges while they're polyatomic ions, but that's a difference of 1 H positive. So bingo, that would be terrific. And then our last one's sneaky. This is very sneaky. This is a difference of 1 H positive, but the problem is H2SO4 is not a HA, a weak acid. It's a strong acid. So unfortunately, you need a weak acid and its conjugate base, not a strong acid and its conjugate base. So that would not work either. But I think you'd identify that wouldn't work when you were trying to actually do the math on this, because you wouldn't be able to find a Ka to turn into a pKa for sulfuric acid. Okay, so let's go and try to, this is a question that you might have to do in lab someday. You might be working somewhere else. Maybe you're working in a biology lab or a biochemistry lab or some other lab where you need a buffer to do the other thing you want to get done. So we want to make a desired pH buffer of 13. So here are our 4 items, well, not 4 items, but 4 Kas available to us that are attached to weak acids. So the weak acid that actually is going to give you a pKa closest would be that one. If I would run the numbers on that, and I would go 4.8 times 10 to the negative 13th and hit the log button, I would get 12.3. Now there's a lot of numbers on my calculator, and I would leave those all on my calculator, but for sake of shortening this so I could write this down, the pKa of 4.8 times 10 to the negative 13th is 12.32. So if we were going to try to figure out how much of the two components we'd need, we would have pH of 13 equals a pKa of 12.32 plus log of A minus over HA, and solve for those ratios. I'm going to have a lot of this written on a separate document because I don't have a lot of room right here. But our two chemicals in question, the HA needs to have that in it. So here I have a list of 8 chemicals that I could pick from. And I need something that has HPO4 minus 2 in it. And that right there has that. So that is my HA. So I can't go get a ion in the stockroom. I have to go get a chemical that has that ion in it. And then I need an A minus that is 1 less H from what I just looked at. And so that would be that. Now you could do all the math right, but if you go pick 2 chemicals other than those 2 chemicals, or even if you do pick those 2 chemicals but get them mixed up for the A minus and HA, again, your math might be perfect, but in practice, that buffer that you created will not have a pH of 13. So you have to pick the right 2 chemicals. Many of these chemicals on this list can also create buffers, but not the buffer that we're trying to make. Okay, so we're supposed to make 100 milliliters. Turns out that that is a very insignificant part of this math. Okay, because the ratio of the A minus to HA will not change if it's in 100 milliliters, if it's in 50 milliliters, if it's in 1,000 milliliters. So let's go, I'm going to go find the math on this. And here's my math. So let me go and turn this into a, yeah, let's do that. Okay, so we needed a pH of 13. I told you that the pKa was that. I told you what 2 chemicals we'd have to go find. I also told you we're going to have to use the Henderson-Hasselbalch. And we'd have to solve for this A minus to HA ratio. And so there is our ratio. Now technically that is 4.79 molarity per 1 molarity. But because they're in the same beaker, they're going to be in the same volumes. So it doesn't matter if it's molarity or moles. I think for mathematical purposes, it might be a little bit easier to think about this in terms of moles. Okay, it's up to you. Now, if I take that 4.79 moles, let's go back to my highlighter, and I go find the molar mass of the sodium phosphate, I would get this huge amount of grams. 785.27 grams is what I would need to weigh out. Could I possibly weigh that out and dump it into 100 milliliters and get that to dissolve? Impossible. Impossible. So that doesn't mean we've done anything wrong. We're just going to have to change our numbers but maintain our ratio. We'll do that in a little bit. So then I had the 1 mole for the HA, and I found its molar mass for the Na2HPO4, and I get that dramatically huge amount also. So that's practically 1,000 grams of chemical. First of all, a lot of stock rooms aren't going to even have that many grams of these chemicals, and then 2, you wouldn't be able to dissolve it in water. So what are we going to do? So all I did was I divided this by what I divided it by 100. And if I divide that by 100, I would have to divide the other item by 100, so I would maintain that ratio. And so you could be able to dissolve 7.852 grams and 1.420 grams into that 100 milliliter container. And I think that might be it, yeah. Okay, so I'm going to go back. Okay, so if you need to go back and look at that, just rewind a little bit there. And the second question, I may not do it in quite the same detail as I did the first one, because some of this is just finding molar masses and converting moles to grams and so forth. So this one, I needed a pH of 7. So pH of 7. So let's think about the Henderson Hasselbalch. Okay, so 7 for pH. I would want a pKa that is as close to 7 as possible. And I think that that Ka is going to get us closest to that. So if I put 6.2 times 10 to the negative 8th and I hit the log button, I get 7.21. And then I can solve for the ratio of A minus to HA. And that ratio comes out to be this time, again, technically those are molarities, but we can easily do moles. Now, it has been told to us that we need to be able to neutralize 0.1 moles. Well, we can neutralize 0.617 of acid with our conjugate base that's in there in that math. And we can neutralize 1 mole of hydroxide with our weak acid that's in our ratio. So let's get those numbers down so that we have actually a ratio that's the same but much smaller numbers, that it's going to be closer to that 0.1 idea. So I'm going to set up a proportion here. 0.617 divided by 1 equals, I would want this number to be able to satisfy my question, 0.1, and then I don't know what this is, so I would just have to solve for that. And when I solve for that, that will come out to be that. So 0.617 is the 0.617 to 1 is the same thing as 0.1 to 0.167. Sorry, 0.162. Sorry. So this is my A minus and this is my HA. So what materials would that be? So this is my weak acid. So I need something as H2PO4. There it is. So that's my weak acid, and then my conjugate base has to have 1 less H than that. And there it is. Okay. So then you'd have to go and convert 0.1 moles of A minus, convert that to grams. So you'd have to find the molar mass of Na2HPO4. And then the other item would be the 0.162 moles of HA, and convert that into grams. And that is with that molar mass of NaH2PO4. And then dissolve that into your beaker of water, and that would have a pH of exactly 7. The rest of these questions are, I think they're all multiple choice. So it looks like we have 4 different acids here. They have 4 different Ka values. And it said, which of the following pairs of chemical species, when combined in equimolar amounts, results in a buffer with a pH closest to 7.5? So basically what we just did, but now remember that you're not going to get the ability to use a calculator to go from Ka to pKa. So it's going to be in the ballpark of those exponents. Not the negative part, but 4, 5, 8, and 10. We want one that's closest to 7.5. So I think we're going to be looking at that. Again, you don't have a calculator, so all we have to go with is that's going to be approaching, it's going to be between 7 and 8. In this case, 7.5. So that's our HA, and then we'd need an A minus. So the A minus has to have one less H positive, so it'd be that. So there we go. We have 100 milliliters of 1 molar HA and 100 milliliters of 1 molar A minus. So that's going to be a perfect buffer. This particular buffer has a pH of 4.73. If you add a little bit of hydrochloric acid, it still maintains 4.73. Why? Because it's a great buffer. And actually why is the hydrochloric acid reacts with the base component. So which of those answers matches up with that? Of course, we already have an answer like we always do. HCl is HCl, or it's H positive, or in this case they have them all looking as H3O positive. So the reason they got that is because of that. They're trying to throw you a little bit of a curveball there. So they all have that, but I guess that's not much of a curveball because that wouldn't have gotten anyone off track. But then you need this A minus, and the A minus is the acetate. Oh, there's the acetate right there. Okay, certainly can't be D. You can't have acid plus acid. That would not work. This is a strong acid, strong base. That can't be A. We don't have that either. Okay, just give you a little insight there. This one looks a little daunting because there actually is 5 questions here. No big deal, but we will have to go back and forth though, so we can see the question and the table. Okay, so number 48. For which acid is the value of the acid dissociation constant Ka the smallest? So that means it has the least amount of forward reaction, the most of the reverse. And remember that HA goes to H positive and A minus. So we would want the one that makes the least amount of H positive. So that's going to be the one that has the highest pH. So it doesn't really matter what column we look at. Well, I don't know. Let's look at this column. Highest pH. Bingo. Let's double check. There we go. Okay. Which of these would be hydrochloric acid? Meaning, which of these would be a strong acid? Remember that strong acids fully dissociate, and so for every molarity of the strong acid makes the same molarity of the H positive. So if you wanted to figure out the pH of that, you just have to do that. So let's look at this one. We don't have to look at this one, but this one might be easy. If you take the log, negative log of 1, you get 0. Which one would have 0? Only the strong acid would have 0. There you go. So that's acid 2. Double check. Okay, we're on track. Number 50. Which of the following species, which has the greatest concentration in a 1 molar solution of acid 1? Remember, acid 1 is a weak acid, and it has the smallest K value. So that means that hardly any of the HA becomes H positive and A minus. So let's go, oh, there we go, acid 1. So acid 1, any of these weak acids, very little of it dissociates. Double check, this was 50C, it was. 51. Equal volumes of the 4 acids at a concentration of 0.5 molar are titrated. So this is a titration question, not a weak acid, strong acid, buffer question, nothing like that. And in stoichiometry, it's all about moles equivalent to moles. Has nothing to do with what type of acid it is. There we go. There's the answer that matches up with that. All the acids will require the same volume to reach the equivalence scale because they all are going to have a certain number of moles associated with them. And double check. Yep, that's good. And we have one more question left. Looks like a doozy. It looks like we have lots of things to write here. We have 25 milliliters of 1 molar, 25 milliliters of, let's erase this so I can see what we're doing here. The same volumes, but the molarities are not the same. One's half of each other. So let's take a look at what that's going to be. So we have HA and we have hydroxide. And that would make H2O, which we don't care about, and A minus, which we very much care about. ICF, 25 milliliters of 1 molar is 0.025, but 25 milliliters of 0.5 molar is half of that. That's special because that's going to make a perfect buffer. Can't fit all those on there. So we're going to have 0.0125 HA left over, and we have 0.0125 A minus that we made. Perfect buffer. If you have a perfect buffer and then you start adding something to the buffer, the pH should not change. pH increases sharply. Nope. Decreases sharply. Nope. Stays about the same. That's possible. Stays about the same. So C and D we like. And why would we like one answer over the other? If we had nitric acid, that's H positive. What component of the buffer would mix with that? It would be the A minus. So which one is that? Conjugate base of acid 1. Answer C, and double check, and it's answer C.